Hi, my name is Arun, and let's continue our journey of mastering graph algorithms. So this is not just to solve this question. This is continuation of what we are learning, graph as pattern. So if you have seen Dijkstra algorithm video and MST algorithm, especially Kruskal, then I think solving this question together will make sense. Okay. So let's continue with this one. So there is this question which is saying that you are having a matrix. Ultimately, there is an implicit graph. So you are having this matrix, and so if you want to go from this 0, 0 cell to this next cell, there is a cost involved, and the cost is absolute difference between these two values. That means 2 minus 1 is 1. So you have to, the cost is 1, or you can say the weight of the edge between this node and this node is 1. Similarly, weight between the edge of this 0, 0 and 1, 0 is 2, because 3 minus 1 will be 2. So this is how implicitly the graph is, and you need to find out if there is a best way to reach from 0, 0 to the last cell of the matrix. Then in that best path, so assuming that this was the best path, if this was the best path, then the maximum weight of the edge in that path will be my answer. So for example, if this is the path, then the weight is 2 here. 5 minus 3 again is 2. 3 minus 5 again is 2. And 5 minus 3 again is 2. So all are 2. It's kind of not the best answer to judge the algorithm to get the question, but yeah, that intentionally they make it kind of dumb in the first example. But if we take any other path, for example 1 to 2, and then my 2 to 8, then 8 to 3, and 3 to 5. In that case, so 8 minus 2 will be the highest edge in this path, right? So if that path would have been best, then 8 minus 2, 6 would have been our answer. If we see this one, so ultimately, so first thing is you have to find the best path. And secondly, in that path, whichever edge is having the highest weight is going to be my answer. Here again, if you see, the answer should be 1 because all are having 1 as difference. In this case, this is the best path. So answer should be 0 because the weight is 0, right? Yeah. So let's just try to understand this. What is the intuition to solve this question? And let's just read the question once, just in case. So you are a hiker preparing for upcoming hike. You are given a heights, a 2D array, size of row into column, where height represents the height of the cell. You are situated at the 0, 0 top cell, and you have to go to bottom right, which is obviously the last cell. You can move up, that means this is 4 directional, up, down, left and right, and you wish to find a route that requires minimum effort. So first thing is that route, best path from 0, 0 to the destination. A route's effort is minimum absolute difference in the heights between 2 consecutive cells. Like we said, the edge of the weight is defined by that. Return the minimum effort required to travel from top cell to bottom cell. Okay, so yeah. Now let's go to our drawing board. All right, so yeah, let's just build. So assume we are having this matrix, right? A, B, C, D are the edge's name, and this is some value given so that we can calculate our weight of the edge. So if I try to build it in a graph, so firstly that will be a better way to visualize this. So A is connected to B and D. I'll try to draw, if I'll be able to draw it beautifully. There are going to be 9 edges, so it will be a good big graph. 9 vertices. So between A and B, I'm having an edge with 2 weight. Between A and D, I'm having an edge with 6 minus 1, 7 edge. And then after that, my the B vertex is connected, B is connected to C. Well, this is my graph. Now, if you see what they are saying, they are saying find the shortest path or the best path, right? So first keyword is shortest path. Whenever we have shortest path, we directly jump for breadth first search. But then my graph is weighted, right? It's a weighted graph. When we have weighted graph and it is shortest path, the algorithm we go ahead with is not breadth first search, it is Dijkstra. All right. So this can be done with Dijkstra. Now the difference is, and that is why I was saying that learning algorithm and solving questions will be able to give us the ideas that how that graph expansion is happening. If we learn that, that will be helpful for us. So will we be able to solve it with Dijkstra? Yes. How? That I'll try to apply Dijkstra from my source, which is obviously always the top cell. So it will be A. And as I'm expanding, I'll not, normally what we do in Dijkstra is we pass that so far the weight of to reach there is 2, then cost to reach there will be 2 plus 1, 3, something like this, right? But what we need to do here is something different, because we need to find that one edge which is having the maximum weight, right? So for that, we kind of keep on passing that one weight, that one edge, that till here that answer is 2, till here also that answer is 2, right? Likewise, we keep on passing. Doing it with Dijkstra, most probably we will fail to code it cleanly, because that standard algorithm is not applicable here. Okay, we'll see you the solution of Dijkstra also. But the point I'm trying to come to, what we saw in our Kruskal algorithm, MST, what we do there is that we build a minimum spanning tree. How we build our minimum spanning tree is from edge. What we do is we select the shortest weighted edge first, right? So here I'm having B and C as my shortest weighted edge. So I'll take that and I'll kind of include that in my answer. Okay, so this will be first it is included into the answer. Then next is I'm having two options, that either I can take this, or in fact 3 options, right? I can take any of this. Let's suppose I'm taking A and B. So A and B will be taken and drawn. When we are doing it, obviously we are checking whether A and B were already connected or not, right? Using our union find, how we learned in our Kruskal algorithm. So what is happening is you are trying to build a minimum spanning tree and you are always picking the shortest edge first. That means whenever your source and destination, in this case my destination is I, right? Whenever your source and destination are connected, you can call it as done. Means till that point only you need to expand your minimum spanning tree. You don't need to solve for the entire minimum spanning tree. One more point, because you are picking every edge in increasing order, because edge are sorted in Kruskal algorithm, that is the first step. That means whenever A and I, source and destination, got connected, at that time when you are processing, whichever edge you are processing at that time, that will be my answer. For example, if I go back to this graph, let's suppose I included this, then I included this. I checked whether my source and destination are connected. No, because only this much of graph is drawn. Then I picked this. Again, is A and I connected? No, there is no path right now, but these different components are drawn, right? So I'll continue. Then I'll draw this. right? Then after this, is A and I are connected? Not yet, right? Then I'll draw this 3. Now, is A and I are connected? Yes. So if A and I are connected, that means what I got is here, if I go back, so what I got is A to B to C to F in between and I. These got connected, and there was an extra edge which is drawn here, which we can ignore, right? But this between F and I, when I connected it, at that time A and I were considered as connected because there is a path from A to I. Whichever that edge is going to be my answer, because that is highest in all of the edges I have drawn in my MST. So it will be this straightforward. Okay, so yeah, this is a little bit of I would say twisted question, but if we have done that, Kruskal recently, it is kind of, we can see that how graph expanding here, that can help me to reach to the solution easily. Let's try to code this intuition, this idea which we just had. I haven't tried solving this one yet. Means I solved this question earlier, but I think I did it using Dijkstra algorithm, if I'm not wrong. So yeah, this is okay. All right. Let's try. Let's first do the first part. So, like we said, what on a high level we are going to do, that we will try to run the MST Kruskal algorithm. So we will build MST until my source and destination is connected. So what do we do in Kruskal's algorithm? If I can just write the high level steps. First, we sort edges by weight. Obviously by weight, that's the only thing makes sense here. Then for every edge, for every edge, we check if 2 vertices already connected or not. If 2 vertices are connected or not. If not, connect, right? When we will do it, at the same time, we will simply check, is source and destination now connected? If yes, this edge is our answer. As simple as that. This is what we need to do. So we know that to check whether edge is connected or not, we basically 2 vertices are connected or not, we need union find for that. That is what we have seen in our Kruskal algorithms video. So let's just try to write these steps first. So what we said is, what I'm going to do, I'll say my edges sorted edges, assuming that I'm having edges where at this place I'm having the weight of the edge. So obviously we'll build that edges array first. Build edges array, okay, from the given matrix. Now once this is sorted, what I'll do is, for every edge in edges, I'm going to do one thing. Let's call it V1, V2. These are the 2 vertices of the edge. This is not the final line, obviously I'll write the line. Yeah, so we have 2 vertices. What I need to do is I need to check that in my union find, so assume I'm having a find, so I'll do find V1 equals to find V2. This is to check whether these 2 are already connected. If these 2 are already connected, then just continue no need to do anything. Yeah, no need to do anything. If not, then we will do union of v1 comma v2. Okay, after every time we are connecting every two nodes, there are chances that source and destination are now connected. So what we are going to do, again, we will run the same condition which we did earlier. If find my src is equals to find destination, if they are connected now, then simply return the answer. The answer is basically the weight of this edge, assuming that my edge is having v1 v2 and a weight also. Okay, this is going to be my answer. In the end, if they never get connected, which will not be the case, but just in case, we'll say -1, because as per given this thing, they will obviously always be one way to reach from top cell to bottom one. Okay, so this is what we need to do overall. This is what we discussed. Okay, now we need two things. First is the things which we need to do inside this method itself, that I need something called edges. Right now the only thing I'm having is a matrix. So edges, how should I build edges? So let's suppose firstly I'm having edges as an array, then for every I in rows, so let's call it length of this is my rows, number of rows. Bottom cell edge, right cell edge. Okay, so far we did nothing but just calculated our edges so that we can have edges array on which we will do the MST. So like I said, this guy will give me a sorted by where my weight is at the second place. So cell address second cell, and the weight is in the second place of this edge. Okay, so this is done. Now we need union and find. So what we will do is we will build our union find. So class disjoint union find set. I'll define where what we need to do is first we define the size of union find. So this time I'll write the simpler implementation of union find. I'll not use I'm not going to use the key, or you can say for compression we use the height of the tree. That I'm not going to use, so that the implementation is simple. So we need a size, and whenever we have the size, we'll simply define an array. We will call it parent. This is by default having for I in range of size. So what it will have is ultimately, let's suppose if this is the array of 3 elements, so it will contains 0, 1, 2. That means every element is parent of itself in the beginning. We need two functionality from this class. One is my find. I'll call it self and you just send me one vertex. We are calling it u, and it will do what? If the parent of u is equals to u, so till the time it's not the case, if this is not the case, then what I'm going to do is that self dot parent of u is equals to just find the parent of u. Whatever is the value, just find the parent of that. So recursively it will ultimately find, and I'm simply going to return self dot parent of u. So this very high level algorithm we have seen in our implementation of Kruskal algorithms. I think that is what I'm trying to apply again. In union, what we will do is we will get two vertices u comma v, and we just need to join them. So there we were doing join by rank, but that I'll skip this time for simpler implementation. So union, what we will do is let's call parent of v as self dot find v, and parent of u self dot find u. Once this is done, then I'll always do self dot parent of, let's suppose pv is pu. So I'm always making u as parent of v. So what happens there is it will be almost a flat tree, because I'm always assigning the root. Okay, so this is the simplest implementation of union and find, right? So I'll go ahead with this one because I think our constraints are very small, so I need not to worry about it because there are only 100 cells. So even if this is linear, and I'm linear, I'll do what do you say, n square times, so 10 to the power 2, and cube of that will also be less than 10 to the power 9, so it will be 10 to the power 6 only. 10 to the power 6 can run within a second, so that I can I'm not worried about it. Obviously this can be almost constant. We can do that level of optimization in union and find, but that's not required here, so I'll keep it simple. Okay, so once we have this, now I'll use our DFU. So let's call it DSU as the object of this, where I need to find out the size of my DSU should be. So it should be rows into columns. That many number of cells will be there. So this is the size, right? And ultimately what we were having is DSU.find, DSU.union, and same thing. Is anything pending? No. Now, obviously one thing I need to change. Basically this is made for, it is considering that your u and v are nothing but numbers, right? That is how I will be able to check it into my array, that at this index, what is the value. But reality is, in our case, u and v are two different cell address. So it is like two dimensional. So you have 0 and 1 will be the value in my v1, and u and something 1 and 2 will be the value in v2, right? So in that case, we need to do some changes here. So to convert this two-dimensional into one-dimensional, I'm going to use a formula. I don't know if you remember that in some first classes of our coding, whenever we started metrics, there we used to study that formula, that ultimately what do we have here? We have 0, 1, 2, 3, 4, 5, 6, 7, 8. These are the numbers we can give to the cell. So there is a formula to convert that I comma j into that number, that how 0 0 is actually 0th cell, 0 1 is actually first cell, right? So we'll use that formula. So let me write that formula here. This is to convert that 2D into a simple number. So this is node equals to, you can call it the number is equals to I into columns, how many number of columns we are having, plus j. Once we are having this, what exactly we are going to use? So this here directly I can use it. So that will be my node. So wherever I'm having I comma j, I'll simply call it node. And then here, let's call it neighbor or child neighbor, whatever we want to call it, adjacent cell. So how I'm going to calculate it is I'm having I plus 1 into columns plus j. This is my first child, and the second one here is I plus j plus 1. All right, so that number we can directly pass. So here it will be child, node and child. This is node and second child. Okay, so now it got converted from my 2-dimensional to 1-dimensional edge. So now the edge object is now having a number which is 0, then child which is 1. Here it will be having number, node which is 0, and child which is 0 1 2 3. So 3 will be here, right, in case of the first cell. That is what we are putting here, right? Now the sorting will be done, and when we will get it out, so what we will get? We will get two vertices, which is 0 and 3 or 0 and 1 with a weight of that edge, and ultimately it's just the normal algorithm. So let's just see if there is any typo anywhere. Oh yeah, so here I just ran the loop but didn't assign the value. Let's just see if there is any compilation error. Oh, which line? Okay, this I can remove. Another typo. Oh yeah, we have not defined the source and destination yet. So let's maybe calculate that number here. So my SRC is always 0, I know. And my destination is, again, we are going to use the same formula. What is going to be my I is rows minus 1, and j will be columns minus 1. Okay, looks like the basic is working. Let me just submit it. Okay, so some edge cases I'm missing. So in case of only, okay, the first basic edge case, basically if your source is the destination itself, if there is only one cell, then that case we can cover easily. In fact, if I just return 0, then this case will be covered anyway. But let's just do it in the right way. So I will add this condition. If my row is 1 and column is 1, that means I should return 0. And here, was it talking about the case that I should return -1 by any chance? No. And I think anyway it will work. So I'll just submit it again. Perfect. So yeah, this is basically the usage of MST. But not, it was not directly asked as MST, and by default it doesn't feel like this is an MST question. Even when you know Dijkstra, only when you know Dijkstra and algorithm, then only will be able to come up to the idea that yes, it looks like Dijkstra. But if you have followed that entire pattern, then you might be able to understand the difference. That okay, I can use MST also, and this is the way to do it, right? So first thing is, if you do not even know Dijkstra, you will try to do something with BFS, and obviously it's unsolvable because this is weighted edge. But if this is weighted and you know on weighted I use Dijkstra, then the next hurdle is that you have to tweak the algorithm a lot to run it via Dijkstra. And the cleaner solution was that do a simple MST here, and building an edge, then it's just more of coding rather than there is no algorithm, there's no pattern in this. This is basic, clean, simple, normal coding, right? Before we move on, let me show you. I actually tried it with Dijkstra also earlier, so maybe I can show you that directly. So what do we do in Dijkstra? Dijkstra means nothing but you use priority queue in place of queue, which we do in our breadth first search. So in this case, when we are doing the priority queue, what do we do here is we check that if the new cost is less than the existing cost of the new cell, then add it into the column. Whatever is the weight of the current edge which we are processing, plus whatever was the cost to reach till there, So, but here the difference is whatever is the weight of my parent node plus whatever is the weight of the current edge, right? Whatever is the maximum of that is what we are trying to put it into the new cost. Now seeing this code, it looks that, okay, in place of plus, I'm just doing a max. Visualizing that is not easy, right? Because I did this question from multiple angles, then only I would say I know it, right? To come to this point in the interview will not be easy. Visualizing that I'm always going to pick the max and I'll carry that max edge till the end of my answer is not that intuitive. Okay, so that is why Dijkstra may lead us to the wrong solution in most of the cases. Okay, cool. Let's just try another question.